are glad and we are very happy because we have the honor to count with two personalities. So we have Dr. Sandy Knowles from the University of Birmingham, and we also have Dr. Mohammed Naim for the same University of Birmingham in UK, in England. So we will have two seminars, 1 hour each seminar. So each one will be of about 50 minutes, and then we will have a couple of minutes for questions and answers. So if you want to ask anything related either to the content of the seminar, or for example, if you want to introduce yourself, if you want to do an academic stay with Professor Sandy or with Professor Naim, then you can also talk to them. So I will introduce Professor Sandy Knowles. He is a professor in nuclear materials from the Royal Academy of Engineering Associate Research Fellow, and from the UK Research and Innovation Future Leaders Fellow. He's also in the School of Metallurgy and Materials in the University of Birmingham in the UK, and he's also a visiting fellow at the UK Atomic Energy Authority. So as you can see, he has plenty of experience with nuclear materials. He is also an expert in metallurgy, so I'm sure that you will be very happy with this talk. So Sandy started his career with a 4-year materials and engineering science master from the University of Oxford in the 2011 with master research on aluminum metal matrix composites. And he turned coated into a PhD at the University of Cambridge from the 2011 to the 2015, and the topic was on novel refractory metal alloys. And he was linked to, the project was linked to Rolls-Royce, and then Sandy moved to the Imperial College London, and he made a postdoc stay from the 2015 to the 2016 on titanium alloys. So he received then a EPSRC Doctoral Prize Fellowship because of his outstanding work, because of the development of BCC titanium superalloys. Posteriorly, from the 2017 to the 2019, he held a Eurofusion research grant to do research on nanostructured tungsten alloys for fusion, and this was held between the Imperial, the University of Birmingham, and the UK AIE. So currently, Sandy started his lecturer position in the University of Birmingham from the 2018, and he has many awards because of his work, including the award from the Royal Academy of Engineering. So this is as a research fellow of the UK Research Leaders Fellows. And he also has awards from the European Union and also from the EPSRC, among so many other awards. So use this opportunity to learn a lot from Professor Sandy Knowles. Thank you so much for being here with us. Please help me to welcome Professor Knowles.
Thank you very much. Thank you very much, Liliana, and thank you very much all for coming to listen. So yeah, and I'm blushing a bit, too many award things. I don't get such a big spiel, but yeah, I enjoy the research, and I've had a lot of good opportunities in the UK, and certainly in fusion, there's a lot of exciting work going on internationally and in the UK. So as Lily said, so I'm a professor of nuclear materials. I'm also on a number of research fellowships. So these are block grants, which go to make me largely research focused in my work, but I'm also doing lectures as well into the topic of nuclear materials. So today I want to talk a bit around the different topic areas. So I want to give a bit of a motivation as to why we might be interested in high temperature materials. So this is looking at applications in aerospace and energy generation, and specifically into nuclear. So thinking about some of the challenges we have when we try to design high temperature applications. So I particularly spend a lot of my time focused on phase diagrams. So the understanding of how different elements might interact with one another, and how we can use this understanding of phase diagrams and the kind of standing on the shoulders of giants, all the prior knowledge that we've had, where over decades and decades, maybe 100 years of research, we've looked at phase diagrams, we've seen how elements mix together, and we can use this knowledge to design new materials. So in some of this can be a bit more empirical. We can just look at a phase diagram, and in more modern methods, we're now using computational engineering in order to be able to do integrated computational materials engineering, which is then when you use computers and modeling in order to design the new materials. So I want to give some examples of some systems that we work on. and introduce this so-called concept of bcc-super alloys, which has been a key topic area for me in my group and my career. So a lot of the funding, maybe more than half of the funding we have, is on this concept of. Yeah. That's all good. Yeah, no worries. Does this, if someone's like it's too loud, then just great. So yeah, I'll talk around these concepts we have in BCC superalloys, which is the key topic area of my research group. And we have these different systems where we can take this microstructure concept and apply it to different base elements. So we can look at titanium alloys, we can look at tungsten, chromium, or ferrite iron. So a lot of the talk today, I'll be talking about these BCC superalloys, and then I'll also introduce and talk about some of the work we're doing on high entropy alloys, which Naeem will also talk about. And that will be kind of a summary of some of the work we have in the research group. So there's about 10 to 15 people in my research group at the moment. So we have people in PhD level, on postdoc level, also undergraduate and bachelor students in the research group. So we're kind of very excited of these kind of new topic areas. So for me, I spend a lot of my time thinking about energy and how we're going to kind of solve the climate emergency that we face at the moment. We see that year on year, temperatures are getting hotter and hotter. And as engineers, what can we do about that? So for me, in the UK, we have an interesting situation that now we build huge numbers of wind farms. So the UK is kind of lucky. We have a lot of coastline, so we can build wind turbines offshore, and that works. It's pretty cost effective. But this was an example day, just when I happened to take a data grab. So there's this website, apps.energy, apps.co.uk.com, where you can go on and see like a map of the world and what energy they're generating and what it's from. So in the breakdown here, whilst in the UK we have maybe 15, 20% nuclear, in some days we might have 50 or even 70% of the energy generated by wind. But on this day, there was no wind. And in the UK, you can have periods where there's 3 weeks with no wind. And if we don't have wind, then instead we burn gas. So whilst the UK has spent a huge amount of money on building zero carbon wind turbines for energy generation, we still are burning a lot of gas. And at other times we're importing energy from our neighbors. So at the moment, in this example, we were importing a lot of nuclear energy from France. I was trying to work out for Mexico. So I see a lot of the work is also in very important sectors on oil and in gas. And certainly for the UK and many other countries, gas is going to continue to be a really important energy source. So we need to do new things to improve the efficiency, as well as look at alternative power sources. So I guess for Mexico, solar is going to be really important. So whether that's photovoltaics, or also in my research group, we also work on concentrated solar power, which I'll introduce later on. For me, one of the examples of why I work on nuclear energy a lot is France. So France is 70% nuclear energy. It's been that way for the last 30, 40 years. They have some of the lowest carbon intensity for energy generation in the world, and they make money doing it. They have the cheapest energy in Europe. So for me, it works. We know it works. It worked 30 years ago. We just have to commit to do it. But in this, there's challenges, and as engineers, we have to try and solve those challenges. So in gas turbines, we can think about these for jet engines. So I do some work with Rolls-Royce, which are a jet engine manufacturer in the UK. I think it's crazy numbers. In the UK, they employ 1 in every 250 people. So as materials scientists, we spend a lot of work, a lot of people work for Rolls-Royce doing jet engine research, but a lot of the technology directly transfers into gas turbines for power generation as well. It's the same gas turbine section, which you kind of use for thrust or for electricity. And we've seen this huge improvement over the years in terms of reducing the amount of fuel that we burn in order to get a certain amount of energy. So this is fuel efficiency in jet engines, or just energy generated if we're thinking about gas turbines for land-based. And so this is really underpinned by what's going on in the engineering, but also specifically the materials engineering. So we can think of different alloys in nickel-based superalloys. So in these, we've kind of seen this progress over the decades, and we see this gradual increase and improvement in the turbine entry temperature. And if we're doing this, then we can kind of think, okay, well, where are we getting to? When we look at these current nickel-based superalloys, we see improvements in the turbine entry temperature from the engine and the kind of engineering improvements, so thermal barrier coatings, cooling channels, these kind of things. But still, we want to improve the base substrate material. And at the moment, when we look at nickel-based superalloys, it's kind of coming to a plateau. And so there's this big question, okay, well, have we just hit the physical limit? Is it as good as it gets? We're not going to get any better? Are we going to see some kind of limited improvements in this kind of iterative, kind of more blue line where we're gradually seeing improvements? or could we instead try to look for something where we can see a step change in performance? And so in my research group, that's one of the things we're trying to do, is there's something fundamentally different we can do to design the materials for jet engines. We also work in nuclear fusion, so I spend a lot of my time working on fusion energy. I'm a visiting researcher at the UK Atomic Energy Authority, which works as a kind of fusion national laboratory. So JET, which is the Joint European Torus, which has been hosted in this center in Culham for the last 25, 30 years. This still holds the kind of record for fusion energy. That one's now just coming to the end of its kind of research time. And we're now building in the south of France, ITER. So ITER, the International Test Reactor. So I was very lucky enough with Can and Tom, PhD student and postdoc from my group. So in January, we were able to visit this thing, and it's really crazy. I mean, this thing costs, I think, $20 billion. So it's pretty expensive. And when you spend $20 billion, it gets pretty big. Like, it's a massive, massive structure. So this is kind of as big as any commercial nuclear power plant or large energy power plant. So the size of this is kind of a 3-story building. It's really, really massive structure. And it's going to be probably the next 5 to 10 years, it's going to be finished building. It's been built for the last 10 years, so probably 15 years total time building. And then we'll get first plasma, hopefully about 2030, maybe more like 2035. But the key aim from ITER is that that will generate net energy out. So we can then know from a fusion reaction that we can use this to kind of create the holy grail of energy, to kind of almost have unlimited energy without much waste. So it doesn't create long-lived radioactive waste like we have with current nuclear technologies. And then there's next pathways for this. So demo, which would be then the demonstrator reactor and a kind of something which could almost send power to grid, is not anticipated until 2050. And so now there's a host of private companies trying to do this. So I think across the world, but particularly with major focuses in Canada, the US, the UK, there's private companies that now have invested about $5 billion into private fusion. So there's individuals, private investors, venture capitalists who think fusion is going to happen very soon. So within the next 10 years, they're proposing that they're going to have net energy out and energy to grid, which 10 years is too soon, but I think in the next 20 years, there's pretty good odds that fusion is going to happen. So what's the problem? I mean, part of it is about getting the plasma physics. So you need to get the conditions of the sun, which is fusion. So you need 150 million Kelvin if you're going to do it on Earth. So it's pretty friggin' hot. And you need to confine your hydrogen isotopes in close enough proximity that you can have the fusion reaction. So some of it is plasma physics challenge, but then we also need to build something which is a functioning power plant. We need something that's going to last and survive for 20 years. So this is where the materials come in. And when we look at the materials that we might use for fusion, we might use steels, stainless steels, reduced activation ferritic martensitic steels, vanadium, tungsten. And all these materials have a bit of a temperature window by which we can use them. So at high temperature, things become soft, or you get creep processes. At low temperature, you get irradiation and embrittlement. So if you irradiate a material, you damage the lattice, and that can lead to embrittlement of the material. So you increase the strength, but reduce the ductility. I mean, so the research group, we tried to look for new materials that might solve both of these problems. So we look at new high temperature materials just in terms of improving high temperature strength, improving high temperature creep resistance, also when you're irradiating it. But we also look at technologies where we can improve the low temperature ductility and make them more irradiation resilient. So we look at this kind of host of challenges that we have for high temperature materials. It's not just kind of one parameter that we design for. So when we want to improve a material, we often try to look to improve the strength of the material. That's kind of first proxy for a better material. But we can't do that in isolation. We need to also think, okay, well, it's higher strength, but does it have sufficient ductility? Is it enough density? Does it have the environmental resistance? Is it oxidation corrosion? So when we design a new material, we can kind of benchmark against some previous materials, so nickel-based superalloys. When we look at, say, something like an intermetallic-based material or a composite material of ceramics, so silicon carbide or these titanium aluminide intermetallics, we often gain on strength, but then we lose out on ductility or fracture toughness. And so trying to take a material that creates a better balance of properties is a real challenge. So we could look at something in my group, this is what we work on, is trying to look at whether we could try to beat this property balance by looking at something like bcc-super alloys or also refractory high entropy alloys. So in these we might get a small improvement or some improvement in strength or density, but without this massive cost in terms of fracture toughness. And particularly we're looking at whether there's new strategies by which we can design for ductility within BCC metals. So when we think of current high temperature materials, if we look at gamma prime in nickel-based superalloys, so these ones are kind of the state-of-the-art materials used in jet engine materials. They can be hugely expensive. You're happy to use kind of elements like rhenium in them. Nickel itself is already pretty expensive. And in these, the fantastic thing about them is you get the high temperature strength, but also the creep resistance and oxidation resistance. And this critically comes down to the phase metallurgy within the material. So you have this FCC matrix, which gives you ductility, and you reinforce it by this nickel-3 aluminium intermetallic that has the high temperature strength, but probably lower ductility. So you kind of can tie the two together, the high strength of the intermetallic and the toughness of the FCC matrix. So you can get this kind of brick and mortar style microstructure where the cubes are actually the gamma prime, and then the channels in between them, which is the matrix, is then the gamma. And we can produce this by understanding the phase diagram. So the phase diagrams are the mixture of elements. As we add nickel and aluminium together, the regions in purple are kind of the different phases that form. So we have kind of the FCC nickel on one side, and then we have this nickel-3 aluminium intermetallic phase. And if we choose appropriate temperatures and compositions, we can design and we can go from a single phase FCC and we can precipitate this nickel-3 aluminium phase. And this is something that we want to exploit in our onward alloys. So when we think about looking at alternative high temperature materials, we said earlier on that the nickel and nickel superalloys are kind of hitting almost a physical limit. And part of that physical limit is probably based off the melting temperature. If something's molten, it's not going to be a very good structural material. So one first proxy we could use is to try to design and select different materials with higher melting points. So we could move rather from nickel-based superalloys, we could go to cobalt-based superalloys, and there's quite a number of research groups that are doing this internationally. And you can get, again, a kind of gamma prime microstructure where you get the high temperature strength, creep resistance, oxidation resistance. So with cobalt, you get maybe maximum 150 degrees, but it's also not that simple. We could go a bit more exotic. We could go to kind of platinum and iridium. And so with these, you gain more like 200-300 degrees. But I think few people can see the problem of trying to build a jet engine out of platinum. I mean, it might make very good business for the mining industry, but it's, you kind of have armed guards around your airplane. It's not feasible to do something on like kilograms and tonnage scale, but maybe for some niche applications, you might be able to use platinum-based superalloys, and at least as a scientist, they're fun. So I can have fun doing research, but yeah, maybe not useful for jet engines and energy generation. So what else can we do? So we could instead, rather than using an FCC-based material, we could instead go to BCC. So we could look at something like tungsten. So tungsten's got 2,000 degree improvement of temperature above nickel. So 3,500 degrees nearly of melting temperature. But now we've kind of switched from FCC to BCC. So we've gained on temperature. We actually still are quite accessible in terms of cost, but we've switched crystal system. So the question then is it possible to mimic gamma prime, but in a BCC-based system? So is there such a thing as beta prime? So this has been this concept area of BCC superalloys. So if we have nickel-based superalloys, I would call them an FCC superalloy. And these are body-centered cubic. And so we can use all of the different BCC metals that we might be interested in. So from titanium, chromium, tungsten, molybdenum. And then we need to then think, okay, well, we've changed crystal system of the matrix phase, so we also need to change the crystal system of the intermetallic reinforcement. So luckily, there are a large number of intermetallic and crystal structures that do have a ordered BCC crystal structure. So for example, nickel aluminium or titanium iron, they both have this ordered BCC-like symmetry, which could potentially be a superlattice compound for a BCC matrix. So what we need to do then is trying to find out, okay, well, which is our phase diagram that's analogous to nickel aluminium? The challenge is not just having the two compounds, so the matrix and the precipitate, but you need to have the two being in equilibrium with one another. So this was this search to say, okay, we want to have the two phases, so BCC and ordered BCC in a two-phase equilibrium. Which systems exist? So we can go through, we can search phase diagrams, we can also use computational methods. And of the binary systems, there's really very, very few. And so one of the ones that comes out is tantalum technetium or titanium technetium. How many people have heard of technetium? It's not a very common element. It has no stable isotopes. You only really get it through nuclear reactions. So again, like platinum superalloys, not going to be very useful if we need to make a jet engine out of it. But again, I'm still just amazed that someone did the test to look at titanium technetium. It's kind of a crazy thing to investigate. But we need to then think, okay, well, are there other systems? And so this is what I've spent a lot of my research career doing, kind of both from my PhD through to my postdocs and now as faculty and my different students and researchers in my group. We've been looking at different systems where it might be possible to have a BCC superalloy. So I'll talk through each of these different systems in turn and some of the students and researchers that have been working on them. So starting off has been trying to look at using a titanium base. So in a titanium base, there actually is in the titanium ion system, you can have BCC titanium at high temperature in equilibrium with this titanium ion phase, which is a ordered BCC into metallic. And so early work from my PhD time, we looked and tried to see whether you could utilize this precipitation reaction. And then Porrick and Vincent, who have been PhD students with myself, have been then kind of digging into the system in greater depth. So with Porrick, we were particularly interested in really, do we understand the phase equilibria? So one of the challenges when we're trying to design these unusual systems that are away from traditional alloys is that very few people have looked at them, and therefore there is very little data. And if you don't have data, then you can't really design anything. To start off with, we tried to revisit just the titanium ion system. I mean, you might think titanium and iron are quite industrially used very widely, both titanium alloys and steel metallurgy. You might think that the understanding of how titanium and iron are mixed together is very well understood, but we found that actually there's quite a lot of people haven't looked into these spaces between the two elements in the great detail. So we looked at both the phase equilibria, so we kind of can take and do things like SEM EDX, so scan electron microscopy, where we can kind of identify the precipitates and measure their composition. We then went into more detail, so these are transmission electron microscopy images, where you can see the columns of atoms and how they're arranged. And we tried to use this as well as then adding in additional elements like aluminium and chromium in order to improve oxidation resistance. So this was one thing with Porrick. With Vincent, we then had a project we were particularly interested into the mechanical behavior of these systems and looking at slip systems. So I'll talk about both of these in turn. So understanding a bit more about the binary phase diagram. So we have this high temperature BCC phase field, we have this intermetallic of titanium ion, and we're particularly interested in this region in the middle between beta and beta prime. So you have the two phases in equilibrium. And what we found is that we can, if we take specific compositions of alloys and we choose the heat treatment carefully, we can produce these kind of microstructures that end up with this two-phase structure of BCC and then the titanium ion intermetallic. Instead, with Vincent, we then were interested in the mechanical behavior of these systems. So when you deform a BCC metal, you have dislocation motion, and it's typically 1/2-1 type Burgers vector. So you have this deformation mode where you're kind of going from the corner atom to the center body site. And so that allows you some ability to have ductility and toughness in a material. One of the challenges is that in the titanium intermetallic and some of these other intermetallics is that rather than having slip to this body centering position, which when you do that, you swap the two atom types. So you have your kind of A atom on one corner and the B atom in the middle. If you imagine dislocation that goes through that corner, like the diagonal, it's going to swap the atom positions. And so that creates an antiphase boundary, and that has an energy penalty to it. In the case of titanium ion, the atoms really don't want to be dissimilarly bonded so much. They much prefer to have a titanium ion bond than a titanium-titanium or an ion-ion bond, that it instead deforms on 100. So this reduces the fact that you don't form an antiphase boundary, but it's a longest Burgers vector, and the challenge is then you also don't have enough slip systems for full ductility. So with Vincent, we wanted to try and find a high throughput way of screening it. Every time you go and do TEM analysis and a TEM, I don't know, it's anyone who's done TEM microscopy, you lose probably 6 months of your life on kind of one sample. So we wanted to see, is there kind of an easier method of doing this? And we were kind of just in the lab, we'd done some hardness indents, so something that maybe many of you have done in kind of research projects. And what we noted is that at the corner of the indents, you quite often see these slip steps. So these are steps that are formed from the passage of dislocations. And we wanted to think, okay, well, if you have these have a very characteristic orientation. You always see them in kind of very specific orientations around the indent. And the question we had is, if you then know the orientation of the crystal underneath that indent, presumably these slip planes are tied to the slip traces are slipped to the slip planes that are active in the material. And if you know the slip planes, you then also know the Burgers vector. So you might be able to work out and screen for ductility just using hardness and EBSD. rather than having to go to TEM. 2 years of Vincent's life, and we now have this automated code. So he's gone and kind of done a lot of computational design work, developing a code that can script all of this process. So you take an input crystal structure for the material. So you take an EBSD. You could also probably do it from diffraction methods. And then you can characterize all of the slip traces that are around this indent. And so then we can work out the slip planes, and from that we can work out the deformation modes. So we've taken this and applied it to different intermetallics. So we really want these intermetallics that are going to slip on 1,111. So when we look at kind of an iron chromium alloy, this has a kind of characteristic slip of 1,111. So we see a great prevalence of 110 type planes, as well as 112 and 123 planes. So this combination of planes together gives a characteristic slip of 1,111. Whereas instead, if we look at our titanium ion system, this one mostly has slip from 100, which is an occasional 110 as well as 100, which then indicates that we're getting a Burgers vector instead of 100. So we don't have the deformation mode that we really want in the material. And so we now have this indentation method that takes on the order of like an hour or two to characterize the slip behavior of a new material. So we can now iterate composition. We can melt new alloys. We can make also composition graded materials, and we can evaluate the slip behavior. So the next system I want to talk about is on tungsten bcc-super alloys. So we took this knowledge that we had of the titanium system and titanium ion, the intermetallic, and we asked then, could we do the same thing but combining it with tungsten? So now we've gone from a binary phase diagram, we're moving in complexity to ternary systems. So along the bottom here is this titanium ion system. So the bottom right is our BCC titanium. We then in the middle here have our titanium ion intermetallic. And the question we had is that going across this phase space, is there a kind of a two-phase line that goes all the way up to BCC tungsten? So this would make the idea of a tungsten-based superalloy, which would be really cool if it was possible. So we then go in, we make alloys, we choose different compositions, we tune, we try to scan across the phase diagram, so making kind of steps in composition. And so this is an example for one of the alloys we studied, and I think it was kind of 5 to 10 alloys that different compositions we studied. And with this alloy, you have the BCC tungsten, you have BCC titanium, and then you also have this beta prime titanium ion. So there is this equilibrium between these different compounds within the phase diagram. And when we zoom in TEM, what we see is that if we go into these dendrite regions, so the tungsten-rich regions, we see that there are kind of a secondary phase within them. And so we were curious whether that phase might be titanium ion. So we can then so this is transmission electron microscopy again, where we're looking at the composition of those precipitates. So we see that they are enriched in titanium and iron, with the matrix then being tungsten. And then we can do diffraction, so select area diffraction methods, where we go into the TEM and we do electron diffraction, and we can then see kind of characteristic reflections of this beta prime intermetallic. So we both have something that's rich in titanium ion, but also this has the crystallography that's consistent with the titanium ion phase. So in this, we have this method called CalFAD, which is one of the main computational design methods when you're doing alloy design. So one of the things that CalFAD has done is taken in all of this phase diagram understanding and pulled it. So rather than kind of, me just kind of pointing on a dot on a phase diagram, you can say, okay, well that composition, that temperature, you can then read off which phase is present. In CalFAD, so computational phase diagram models and databases, which you can then just plug this in on a computer. You can say, I want to give composition of this with a temperature of this, and it will predict what is the likely phase formation. And you can also then tie that into scripts and do kind of almost like AI-directed materials design. So one of the questions we have often in these BC-super alloys is whether we can do computational design with these new alloys. And one of the challenges is that we don't have the base data. So the model relies on prior data. If you don't have any data, you're not going to do a very good prediction. So for a lot of our work, we've had to go and do things experimentally. You go melt it and really look at it. And then but what we do try to do is to take that knowledge that we've gained experimentally and tie it into a model. So over time, we'll build up predictive understanding. The other side of things is to try and start to demonstrate the properties of the materials. So this was quite what I would call model alloys, so they're still quite simple, so just kind of binary and ternary compositions. But we can begin to look at what kind of properties can be achieved in these materials. So we can look at the flow stress, so the temperature, the yield strength versus temperature. So benchmarking against a 718 nickel superalloy, and also some just pure tungsten. And what we find is this tungsten superalloy, 1,000 degrees C, we're still maintaining half a gigapascal, so 500 megapascals of strength at 1,000 degrees from a very, very simple alloy, like literally just sort of 6 months, 1 year project, and we can already beat nickel-based superalloys and tungsten. So this gives us kind of confidence to continue going down this path. The next system is then looking at chromium-based BCC superalloys. So this is work from Dr. Kanmar and Tom Blackburn, who have been researchers in the group on a European project. So in concentrated solar power, you have photovoltaics, which is kind of maybe what people typically consider as solar panels or solar power. But there's an alternative method where we instead use thermal solar. So in this, you have a massive field full of mirrors. So it can be like 1 or 2 kilometers, big field full of just mirrors, which all focus the sunlight to a central tower. So that's kind of what's indicated on the left-hand side, but there can be maybe 1,000 panels within an array, and they're all just focusing with just a mirror, the sunlight to this central tower. At the central tower, you can then get to really, really high temperatures, so you can melt steel very easily. So you can go to kind of 2,000 degrees if you wanted to. Basically, it just depends on how much coolant you put through, but very, very high heat depositions. And in the technology that's being pursued by our consortium, but also by Heliogen, which is a unicorn, sort of a multi-billion-dollar startup in the US, is to try and use ceramic particles as the heat transfer medium. So they can have good very stability, high energy density, and you can then take these hot particles and you can also store them. So when the sun isn't shining, the particles stay hot, and so then you kind of have a way of storing that energy over time. Within this specific system, we were then looking at trying to use a supercritical CO2 power cycle. So rather than steam turbines, if you instead go to supercritical CO2, you had advantages in terms of the density of the product, but also the thermodynamic efficiency. But if you go to the system and you have high temperatures of 700 degrees, you have supercritical CO2, which also is corrosive, and then you have erosion during the particles. This is like a pretty wicked problem in this kind of heat exchanger geometry where you have kind of tubes with particles throwing over them and then supercritical CO2 throwing through them. It's a pretty demanding condition. And so we wanted to look at what new materials might be able to withstand those conditions. So we looked at this topic area of chromium BCC superalloys. So a similar logic, we're now taking a BCC metal, but instead chromium. And going across in the phase diagram, we can then use the nickel aluminium into metallic. So now we have a two-phase equilibrium going through that ternary. And we can then kind of characterize this. So we form precipitates. So this is in SEM. We can form these precipitates, and then we can go into different advanced testing methods. That was a real kind of advantage of doing this as part of a consortium and like kind of large-scale international collaboration, is that we're then able to do high-resolution TEM, where you can then see the atom columns and how things arrange both in the chromium, in the nickel aluminium, and also at the interface. So kind of trying to design specific interfaces, for example, of the misfit, so how the two lattice planes kind of are coincident, and the misfit and the lattice parameter of the different elements. We also can do things like atom probe tomography, where we can look at the elemental segregation between these different phases. One of the really kind of interesting results within this new kind of materials class of chromium BCC superalloys has been particularly into the coarsening resistance. So we could do things where we kind of anneal at a high temperature and particles will gradually get coarser. So ideally, in a high temperature material, you want things to be quite stable at your use temperature. So if your material is changing in microstructure through time in service, you're going to change properties. So you really want something that's not going to change too much. So what we found is, in comparison to, say, ferritic superalloys, nickel-based superalloys, or cobalt-based superalloys, this new material of chromium superalloys has much slower coarsening rate of the precipitates. So at least in a kind of microstructure stability thing, we've got a big advantage there. We then also were looking at the mechanical behavior of these things. So this is, again, relatively simple alloys. So we have 4 elements. We have chromium, nickel, aluminium, and a certain amount of iron in order to tune the microstructure. And then we can, again, get to very high yield strength at high temperature. So we can kind of get things that are competitive in the case of about 3 years of work with 30, 40 years of nickel superalloys development, which is really exciting. So we're there in terms of strength. We're not yet there in terms of the balance of properties. So within these things, we get good strength, we get good oxidation resistance, we get good corrosion resistance, but we don't yet get ductility. And this is one of the major challenges for BCC superalloys, for BCC alloys, and for intermetallics, is trying to get this combination. You can improve the strength, but do you do it at the cost of ductility? So the last of the BCC superalloy systems is this one class of ferritic superalloys. So we have quite a large number of people working on this in the group. It's quite an attractive system, so we're basing on iron and aluminium. So as you add aluminium into a steel, you reduce the density, so that's quite attractive if you're trying to lightweight automotive into other applications. And again, we're taking this microstructure concept of a BCC iron, this time base, with these ordered into metallics as the reinforcing phase. And you can form these kind of cuboidal gamma-gamma prime-like microstructures, but instead now we're, I guess, alpha-alpha prime, if we're using steel nomenclature. So here we have, again, the interest of trying to develop high temperature strength, but we're also now looking at a radiation environment. So when you irradiate a material, you bombard the lattice sites, you have an incident particle, so that might be a neutron, it might be a high energy ion. And as it hits the particle, hits into the lattice, it's going to disrupt and create a cascade of damage. When you kind of impact and irradiate a material, you tend to create a lot of vacancies and dislocations, which create defects within the materials. So those will harden the materials, but also potentially embrittle the materials. And so what we really wanted to look at is trying to chase this idea of using interfaces as defect sinks. So if you have an excess of vacancies or dislocations within the material, if you have a large number of interfaces, all of those interfaces can particularly act as sinks for radiation, for these defects. So if you imagine you have, say, this is a dislocation at the interface, if a vacancy moves to that region, it can just extend the dislocation line, and you can allow for the annihilation of that vacancy. So if you can reduce this accumulation of defects within the material, you can make it more resilient to radiation damage. And the nice thing about these materials that we work on is that we have this method for understanding the phase diagram to tune the microstructure and design nanostructures where we have a very high interface density. So we've done some experiments looking on this. So this was work in University of Surrey where we did ion irradiation. So you take I guess just a large accelerator, large electric field, and then you can bombard ions into the surface of the material. And then we could then do nanonotation, so a very small indentation method. We can pick up the hardening from that ion irradiation. So this is work from Steve Zinkel and others in the US that have done a lot of work on these kind of so-called oxide dispersion strengthened materials. So these are kind of powder metallurgy-based route where you can create very fine-scale microstructures, but it's a technique that's quite hard to do repeatably and also very hard to scale up and also just very expensive. For us, we're using a relatively cost-effective casting, like a typical casting method, the same as you would see in a normal casting foundry, but just at a lab scale. And what we can do is by creating this nanostructure in a ferritic superalloy, we can get to the same level of fine-scale microstructures that we see in these oxide dispersion strengthened materials. And if we can get to those very fine-scale microstructures, so this kind of result here is when we irradiate the material, we see no apparent irradiation hardening. So this is kind of quite a profound result that normally when you irradiate material, you create defects, they strengthen the material, but they harden and embrittle material. It's quite unusual. It's only really in these ODS materials and these ferritic superalloys where we've seen this almost nil apparent irradiation hardening. So we're quite excited for this result in terms of being able to develop more irradiation resistant materials. So within Birmingham, we're very lucky. So within my lab, we do a lot of work on the kind of phase metallurgies, so producing alloys, doing characterization, using advanced characterization methods, so SEM, TEM, and then we also collaborate for atom probe tomography. Then do kind of mechanical testing, this kind of thing. The other thing which we're very lucky for in Birmingham is that we have a very strong physics department, and within that they kind of do a lot of particle accelerator style work. And this includes something called proton irradiation. So we have a cyclotron, so we can accelerate protons within electric field and large magnetic confinement, and we can irradiate the material with protons. So if we do this, we can do a different method of studying how the material behaves in a best to simulate a nuclear environment. As well, we also have a neutron accelerator, so we can bombard materials either with protons, light ions, or with neutrons in order to simulate irradiation damage. So the last topic area I wanted to talk about was this topic area of high entropy alloys. So this has seen a lot of interest in the academic community recently. So in metallurgy, it's definitely a very popular area. And we're going to talk about a little bit what they are and some of the work we've been doing on them. So in a high entropy alloy, you can have other phrases to define them. So they're also known as complex concentrated alloys, multiple principal component alloys. But the key concept is rather than having a pure element. So previously we've talked about tungsten alloys, titanium alloys, steel alloys. In this, we instead try to look to something which is a combination of elements. So if we look at, say, this kind of pseudo-ternary, we have A, B, and C. This might be kind of pure elements. But instead, if we mix them in kind of equiatomic concentrations, we get something different in the middle of this phase space. And the thing which was particularly unusual about high entropy alloys is that when you mix multiple elements together, as we saw in some of the kind of previous work in the kind of binaries and ternaries, you often get intermetallics. So say, for example, we added chromium, nickel, and aluminium together. Okay, well, we formed a two-phase equilibrium which contained BCC and nickel aluminium as an intermetallic. What's been quite unusual in quite a number of the high entropy alloys is that you're possible to form a simple crystal structure, be it BCC, FCC, or HCP, within this complex composition space. And that gives kind of us a new design rule in order to be able to make new materials. So the idea here is that we've got a simple crystal structure. So we've got a large number of elements, but a simple crystal structure. So this means we have very, very different properties in that material compared to a pure element. So there's a few things that we have as ideas here. So we have this idea of entropic stabilization. So this was the idea that when you mix a large number of elements together, you increase the entropy, which is going to then counteract your enthalpy, which is kind of trying to form intermetallics. We have a large number of elements that are mixed together, so you've got a huge amount of solid solution strengthening, so you're getting this potential high strength. It's been observed that you also see kind of quite sluggish diffusion within the material, and then you also get some cocktail effects, so there's interesting things, particularly say in terms of irradiation resistance. So why high entropy alloys? I mean, they're potentially a curiosity. The particular interest is that they have observed some properties that we haven't seen in any material that we knew previously. So for example, I guess, and Amy will give it in much more detail later on, around the cryogenic toughness. So particularly this system, chromium on the right-hand side, chromium, manganese, iron, cobalt, nickel, has shown almost the best combination of strength and ductility at cryogenic temperatures of any material that's known. And from that, we kind of have a new design logic as to how to design materials for cryogenic applications. If we look instead of this refractory high entropy alloy, where we have niobium, molybdenum, tantalum, and tungsten, we're also in this system seeing higher strength than any of our refractory metals in isolation and higher than nickel-based superalloys. So in this, again, we have a new design rule for high temperature, designing for high temperature strength. And in this last system, then we're talking chromium, vanadium, tantalum, tungsten. So this is, again, an article from Science Advances just a few years ago, where we're seeing very, very little irradiation hardening. So in terms of the irradiation resistance of high entropy alloys, there's something about when you mix the elements together in this complex way that you get massively improved properties some of the time. It's not a guarantee, so not all high entropy alloys are fantastic. Some of them are terrible, but some of them show these kind of behavior that is really doesn't exist in other materials. And if we can understand the mechanisms for that, it can really help us try to design new materials. So this has become a huge, huge area internationally. So now kind of year on year, we're seeing like over 1,000 papers published a year by the community, which is a big increase compared to any other sector. So certainly this is one of the kind of fastest growing areas of metallurgy, I would say. So probably a similar thing 5-10 years ago, we saw a similar trend, say, in additive manufacturing was a huge growth trend. Now probably, I don't know if we've seen peak additive, but we're certainly kind of close to it. Whereas in high entropy alloys, it seems to be growing very quickly. And over the last couple of years, so I've spent most of my time working in refractory metals, is we've seen a big growth in the refractory high entropy alloys. So the question is, what do you do? So how do you design a high entropy alloy? A high entropy alloy can just be defined by mixing different elements together. So we could take a dartboard and we could just throw darts at it and we could pick 5 elements and that would be a high entropy alloy. And I think this has kind of been done. Like if you go in the literature, like there's lots of different mixes. You know, you have a paper which is, okay, we'll do zinc, molybdenum, cobalt, iron, aluminium, and we'll see what happens. And you can just mix it together and you can have some fun as a physical metallurgist seeing the microstructure and seeing what the properties are. So maybe doing it completely randomly is not the best idea, but every so often, you know, we discovered penicillin for a kind of random chance thing. So maybe we should sometimes do some random chance work. Other things we could do, well, we could just say, well, you know, Brian over there, and he did some great work, Brian Cantor, and he found this alloy, and Jingwei Ye both found this alloy, cobalt, chromium, iron, manganese, nickel, and that's a great alloy. So you're like, okay, well, let's see if we can make it better. So we could take a good starting point and try and improve upon it. We could use that one methodology. But the other things is, okay, well, can we use some other method to try to develop and discover new materials? So we could use this method I discovered earlier on CalFAD. One of the challenges is that we just don't have the data. We haven't looked at these combination of elements together, so we can't predict very well. The question then is what other methods we have. So there's quite a number of groups working on this, and this was with a colleague of mine, Dan King, who did his PhD on this in Australia, trying to develop a new high-throughput screening method. So for him, he was looking at methods which are kind of effectively akin to the Hume-Rothery rules for whether elements are likely to mix together. So we have one of the parameters, which is just the atomic size mismatch. So if elements are very different sizes, they're probably less likely to want to mix together. And he then developed this phi parameter, which was trying to predict the entropic stabilization, so trying to predict entropy. And when we take this, so this code is really nice. It is technically publicly available, but I think the website link died, but we have a copy of it if anyone wants it. And the idea here is that if we have these two parameters, we can then say alloys in the top left corner are likely to be a single phase solid solution. And this code kind of takes 5 seconds to run. So this was 100,000 compositions and like 5 seconds to run. So it's a very simple code that just uses kind of a data lookup type table to develop, to isolate the different alloys. The interest that he then took in Dan's work, and when we worked together on this, was to try to combine that with another parameter. So that could be melting temperature, but in our case, we were looking at neutron cross-section. So we wanted to develop new materials for nuclear reactors. So within the core of a reactor, you have the fuel clad, so you have the uranium fuel, and you want to get neutrons from one bit of uranium fuel to the next bit of fuel. So in currently reactors, you generally use zirconium, but it has a very low neutron cross-section. But we wanted to have something that would have low neutron cross-section, but also potentially high temperature strength. So we could do this, we could screen and develop and isolate and go from 100,000 compositions to 5. And then within those 5 compositions, quite a lot of the other ones had uranium in them, and we couldn't handle uranium in our lab, so we didn't do those. We instead looked at this niobium titanium system. And then we could take these different high entropy alloys and do some more further study. So we can attempt to use CalFAD. So CalFAD is particularly in this software program called run by Thermocalc. There are FactSage and other providers for these software. We can try and use that, and this will tell us the potential phases that might form with temperature for these specific compositions. In this one, it's probably only 20, 30 seconds, maybe a minute per composition. But if you want to do 100,000, then it's not really feasible to do it on that large scale. Also to interpret the data. But you can, if you're kind of pretty clever, do kind of modeling methods and coding in order to try and loop CalFAD into the discovery process. But the key thing here we had is that, okay, at high temperature it's liquid, then it forms BCC as we go down in temperature, and then we have a combination of potentially second phase BCC, HCP, and this Lavis phase intermetallic. So we wanted to see, okay, well, we have this prediction, does that actually tie up to reality? So we melted up these alloys, a series of alloys, and then we look at them both in the as-cast condition and then after thermal annealing. So for us, this is a kind of marked response that at 1200, there is truly a single phase field, so it is actually a high entropy alloy in terms of that you can get to this single phase solid solution, which is one of the key characteristics of some of the high entropy alloys. So we then can characterize that in terms of what kind of crystal structure that we have BCC, what lattice parameters, as well as what composition we actually produced. If we then go on to thermal anneal it, so for us, we're trying to develop materials for high temperature applications. So we need to know what happens through the use temperature. So when you process it, you might need different conditions, but also when you're going to use it at, for example, in a high temperature nuclear reactor, it's going to sit at temperature for a long time. So we need to know whether it might decompose. So in this case, this high entropy alloy, despite all our entropic stabilization, it doesn't stay single phase. So we do get this decomposition, we do get formation of intermetallics. So for a bit of painful work, we can also do TEM as well as SEM, EDX, and X-ray diffraction, and we can work out which phases they are. So in this case, we do get quite similar phases to what is predicted by CalFAD, but at different temperatures. So the CalFAD kind of gets some of the way there, but it's not enough to really truly design an alloy. It gives us an indication, but it doesn't have sufficient accuracy yet. So this could be a problem. We've kind of failed at creating a high entropy alloy, or we've failed at creating a single phase high entropy alloy. But for us, when we kind of think as metallurgists, the majority of materials we use do have multiple phases in them. So in this case, rather than having something that is single phase, we now have a multi-phase material that is potentially a mechanism by which we can get high temperature strength, high temperature creep resistance, but also, as we kind of talked a little bit earlier, around this potentially this interfaces as defect sink. So potentially this could have a good benefit of trying to produce something that's radiation damage resistant. So we have a range of different work kind of carrying on, trying to investigate different alloys of refractory high entropy alloys. Particularly the challenge is we want to look at thousands of compositions. Like we want to really look in a much wider design space, and how do we do that quicker? So one method is to develop new modeling methods that might allow you to screen and then you do more focused experimentation. The other is to try and look at high throughput experimentation methods. So in this, we've been trying to do multi-composition gradient materials and then mapping techniques so that we can discover more materials in one experiment. And we've also been looking at materials on the right-hand side, which are with low activation. So when you make a fusion reactor, you have a lot of high energy neutrons. If you bombard a material with neutrons, it might transmute and it might turn into a radioactive species, or probably will. The challenge is if you use the wrong materials and the wrong elements within your nuclear fusion reactor, you might create something that becomes long-lived radioactive waste. So you don't have that advantage in fusion than you would over fission. But if you carefully select elements, so basically kind of avoiding the red elements on this is kind of from computational calculations, about which elements are likely to activate. And when alloying, we avoid those elements, we can potentially design new materials that are non-reduced activation. And so this is a big focus effort into the fusion community. And this topic of high entropy alloys and bcc-super alloys has now also kind of caught on in the literature. So we're doing the two topic areas separately, looking at them in isolation. But actually now there's a lot of work which is looking to combine them. So in work internationally now, there's a lot, I think, I don't know, there were 10, with TMS there was about 10 or 20 presentations that we had on this topic of refractory high entropy superalloys. So particularly this system, which is niobium, tantalum, titanium, vanadium, zirconium, aluminium, bit of mouthful. And you can get these kind of cuboidal gamma-gamma prime type microstructures. Cool. So that, to summarize, is this kind of two key topic areas we've been working on of BCC superalloys, where we can mimic this kind of gamma-gamma prime-like microstructure, but in a BCC metal. So we've done a lot of work trying to produce and characterize them and evaluate some of their base properties, but still some work to be done trying to develop adequate ductility. Then on refractory high entropy alloys, one of the key questions is how you efficiently design these materials and discover them, and also if we can demonstrate some of the mechanisms as to why some of them show these really advantageous irradiation performance. So a big thanks to many people in the research group who have kind of helped to perform this work, as well as many collaborators in the UK and internationally that have got involved to kind of take this work forward and support me in my career. And then, yeah, a great many research funders who have supported this work, so particularly this kind of UKRI Future Leaders Fellowships, which has allowed me to work with Lily and Naeem, so that's been a great pleasure. And then, yeah, different grants that we've had that support this work. So it's been a pleasure to talk to you all. Happy to take any questions.
So thank you so much to Professor Sandy Knowles for such an amazing presentation. So we have some time for questions and answers. If you want, you can ask in Spanish, and I will translate in English for you. Pueden preguntar en español, y yo les hago la traducción, okay? So do we have some questions or comments? Okay, please. Just, I will give you the microphone. Wait a minute, we have one more here. I can open it, or you can use it. Just a minute.
Hi, my name is Liz. My question is, how did you make superalloys diagrams? How?
Yeah, so most of ours have been kind of arc melting. So you kind of take effectively a tungsten electrode and a large electric, basically a welder. So you have a welder, but in an atmosphere, and we have this arc melter where we can produce between 10 and 300 grams of material. And in this, we can also melt things that include tungsten.
Okay, thank you.
Okay, first here and then here. Just a minute.
Hi, well, first of all, thank you for this presentation, Dr. Sandy. It was like really illustrative for me. I don't know, I can't speak for the others. My question is, well, you mentioned well, in developing high entropy alloys, you used like calc to make the phase diagrams and try to make the predictions. But as you already said, that is like depends a lot of the available data that we have today. My question is, have you ever wondered? Well, I need to reply my question. Is there any chance for artificial intelligence to improve these things, to make these like simulations without the using the data? So because I mean, like we have a lot of elements and metals and a lot of possible combinations, like as you said, which elements do I choose, or like taking, for example, as you said in tungsten, yeah, I need material that has a high temperature of melting. Well, I can use tungsten, is a good starting point, but I mean, there's a lot of combinations, a lot of elements that making it, I mean, real life, it would take a lot of time. It would be like a waste of resources and money. I know.
No, it's a good point. And I think, I guess in every sector, AI is going to transform things, right? I mean, there will be things, and if you're not on the curve, you're behind the curve, right? You have to see what is possible with AI. It's been interesting in terms of there's a couple of companies that take the kind of CalFAD approach and then link it to physical-based models. So you can use CalFAD that takes from composition to microstructure, and then you can have a physical-based model, so like Orowin strengthening equations, this kind of thing, Hall-Petch, where you then take that model, the equation, and you can then tie that to the properties of material. So they've kind of looped this into a process where you can put in and say, I want this kind of properties, give me material that has those properties. The challenge is at the moment, most of those are really based off CalFAD. So it works really well for nickel alloys, it works really well for steels, but if you go into an unusual alloy like a chromium alloy or a vanadium alloy, if we haven't looked at the phase diagrams, we just don't have the data. So there is an idea that we can kind of AI or machine learning way our way out of the problem, but the challenge is just we don't have the data. And so I think there's two things we can do there is how do we get data more efficiently? So actually kind of high throughput experimentation, where rather than doing kind of one ingot and then we spend 6 months working and we get a data point, can we get many data points at once that we then can feed into the model? And the other one is then to use AI methods, at least at the limit of the ability at the moment. So we have a few corporations where we're using AI materials design and then trying to take that data point that comes out, or a few data points that come out of the AI model, you manufacture them, and then you compare them and say, okay, well, why does the model not work? So can we improve the model by doing iterative experiments and modeling and bouncing back and forth? So yeah, good question.
Okay, thank you very much.
Hi, my name is Brenda, and thank you for your presentation, and sorry for my English. So my question is, do these locations follow a different behavior during low temperature and room temperature, the formation of phases center cube metals?
So the different deformation behavior, high temperature, low temperature, is this?
Uh-huh.
Yeah. So it's an important one. Yeah, I guess in BCC metals in general, we have the brittle ductile transition. So your matrix is not an ideal starting point for something with ductility, because you have to tune and choose your element of the base metal. So chromium or tungsten has a brittle character at room temperature because of dislocation behavior. You can potentially do alloying additions, which can change that. So you can then improve the matrix behavior of the BCC metal. We have the same challenge in the intermetallic. In that one, it's both potentially an opportunity though as well, because we ideally want the same deformation mode as the BCC metal, where we have this 1/2-1-1 dislocations, which can give us ductility. But in nickel-based superalloys, we also want dislocations that when you go to high temperature, they become harder to move. So you have this idea of anomalous yield behavior. So it happens in the ordered intermetallics because as you change temperature, you change the energetics of dislocations and cross-slip. So potentially you can have a trapping mechanism. So you ideally want a material that is ductile and allows dislocations at low temperature, but becomes harder as you go to higher temperature. So there's ideas that we try to do to design around this, but it's quite complicated, yes.
Thank you.
Some other question? Okay. So remember that you can ask in Spanish or English or what other language you like.
You test my Spanish.
Yo tengo una duda acerca de si existe alguna situación, alguna limitación de que haya cementita en alguna aleación de alta entropía que tenga algún acero.
The question is if there is some limitation or problem and if it is possible to have cementite or some brittle phase in some high entropy alloy.
Yeah, it's an interesting one because in this one, say for example, the system we studied where we had predicted to have potentially some Lavis phase and we do observe some of this Lavis phase. And it's a bit of a question around like what is brittle? Like in this sense for us, when we did the work looking at the slip system type with Vincent's work where we have this 100 versus 1/1 dislocation types, if you have the wrong intermetallic and you can't have a dislocation pass from the matrix into the second phase, you might have a brittle failure because the dislocations will just accumulate, the load is created at the interface and you then get a brittle failure. So for things like cementite, I guess it's a question of whether you can have slip transfer from the matrix to the precipitate, but also the length scale. If you make it very, very fine, like as in cementite and perlite, you can get good ductility because you make it small enough that you can still force dislocations through it. So there's some things you can do on microstructure, and there's other things you can do on the fundamental design of the deformation in that intermetallic. In general, we've stuck to these ordered BCC systems because we think we can get a better load transfer and dislocation slip from the matrix into the precipitate. Whereas with a Lavis phase or maybe cementite, if you have a large carbide, it's more likely to be brittle.
Thank you. Do you have some other question, comment? Okay.
So you mentioned that in order to build the model to predict how a superalloy behaves, you have to do experimental work. So do you have like a set of standard steps to get there with every alloy, or you have to do something different with every material?
Yeah, I guess in theory it's like a common process. So we have a process that many people in the research group, and I guess Lily and you will be able to comment on, that we have an approach where we can say arc melt a material, we can then do thermal heat treatments, we can then go into scanner X-ray microscopy, X-ray diffraction, and different methods where we kind of create a base characterization. And then sometimes it doesn't work. And so that's kind of, I mean, that's the nice thing about doing discovery and experimental science is that you have an idea when you go in about what will happen. But sometimes it's not perfect. And then you have to refine your idea and improve. But we try to have a common approach also so that we can compare from one material to another. So if we get a strength from a given material under different given conditions, we know that that's comparable.
Thank you. Some other question? Comment? Okay, 1 minute.
Hi, my name is Luis. My question is, what is role of precipitation in refractory materials?
Which one, sorry? The role of? Okay, yeah.
Yes.
So, good, yeah. So this is like, I guess for us is the key one. And if you have just a simple BCC metal and you go to high temperature, you probably will get something that's insufficient strength. So we need to add the precipitates in order to get the high temperature strength as well as the potential creep resistance. So that's where we do a lot of work trying to do this kind of phase diagram design to understand which phases and which precipitates might form and at which temperature and which composition they form. And are the precipitates the intermetallic phase we really want? So yeah, that's a key question, is like how we design the specific precipitates. Yeah.
Thank you.
Mm-hmm.
My name is Marco. I'm going to ask in Spanish because I have a bad English. Mi pregunta es acerca de si alguna de estas aleaciones podría ser semiconductora. Bueno, más que nada relacionado por la estabilidad térmica que puede tener, por ejemplo, para procesadores.
Okay, so the question is if there are some high entropy alloys that can be useful for semiconductor applications, like kind of optoelectronics, and what about the thermal stability? Because you know, with superconductors sometimes like they can like be high temperature, low temperature, like kind of fatigue.
Yeah, it's a really interesting question actually. So I guess I've mostly spent my research time in structural materials. So most of my work is in like fusion reactors and like the structures. But in this one, I guess there's an interesting one because a lot of the applications of chromium, molybdenum, and tungsten are on wafer like diffusion barriers. So you could imagine that because high entropy alloys are reported of having lower diffusivity, and slower diffusion, they could act as a diffusion barrier layer. So they might be interesting for that regard, yeah.
Thank you. Some other question or comment? Okay, please.
Hi, Professor. Thanks for the presentation, first of all. I was wondering if concentrated solar power could have civilian or urban applications, considering that using superalloys might increase the cost and make it like less viable.
Yeah, it's a real trade-off, and it's been one of the things that's been factored into this consortium we have looking at the concentrated solar power. So within that, part of it is about the engineering design. So we work on the metals. There's another group that work on the ceramic particles and just the durability of the ceramic particles. But the crux thing is around the whole efficiency of plant. And so that was one of the considerations and motivations to look at this alternative route is you say, okay, well, if you build the thing out of some material, if you use a higher performance material, it's more expensive, but maybe the durability is higher or the energy efficiency is higher. And it's a really tricky trade-off. And I think particularly say nickel-based superalloys would be one candidate material here, but they're very expensive. And for this specific application, they're not very good in wear resistance. So that was one of our motivations to look at an alternative to a nickel-based superalloy. But we also quite like the chromium-based superalloys because they would be about a quarter of the price of a nickel-based superalloys if we could make them work. And we know nickel superalloys work very, very well, but you need to have a lot of money to make them work. So there's a lot of work, and particularly say on our ferritic superalloy work, this was originally for supercritical steam exploration. So if you have alternative power cycles for kind of coal or for gas, if you're using a steam power cycle, if you can run at higher temperatures, you can get improved fuel efficiency. And so that's where the ferritic superalloy work started in the US, in the Department of Energy. Yeah, it's possible, and the key advantage is using a steel-based material is much, much lower cost than nickel. So it's a balance of cost versus the performance.
Thank you. I think one last question of comment because we are already out of time. Do you have some question or comment? No? Okay, then just on time. So, 1 minute. I will just give a small present to Professor Knowles for the very nice talk that he gave to us. So, it's a thermo. So it has the logo of the university. So thank you so much. Thank you. And 1 minute. Before finishing, we have a gift for some student. So I will ask to Professor Noodles to make a question for you. And the first person that will reply will have the gift. Okay? So please, you can select any question.
Okay, I'm going to go a difficult one. Is that allowed? Okay.
Sorry?
The slip, does anyone know the slip system in BCC?
Come on, it's an easy one. Check your notes. Yeah, okay?
Is 110? No. No. Or 111? Yeah. Thank you.
Okay, congratulations. Okay, so thank you so much again to Professor Knowles for this amazing talk. As you know, we have a second one, but we have a 5 minutes break. We have cookies and coffee for you like to and then we will come for the next talk. We have more gifts for the students. So Professor Naim will do like different questions to you. And by the end, we will also take a group pictures, like all together at the end of the second seminar, okay? So 5 minutes for coffee and cookies.
Thank you.
How do you feel? Did you enjoy?
Yeah, good.
You have a lot of questions. The students are super interested.
No, it's not.
I hope that you can enjoy all of the university. So you will not forget.
I like it. Yeah, well, yeah.
Sure. You want your computer? Okay.
I know.
Please take your seat.
Yeah, I think you can catch me afterwards.
Yeah, don't worry, Professor Knowles and also Dr. Naim will be here sometime after the seminars, so you can discuss with them. You can take selfies with them. So please take your seat, okay? Okay, so we will start. So before starting, I just want to thank to the professors that attend today. I think some of them are still outside. They will come inside after some minutes. But thank you to Professor Angel that was here, Professor Clara, Balbina, Professor Gonzalo that also came, Professor Luis, I don't know if he's still here, but thank you so much for attending the seminars. And I would like to introduce to our next speaker. So we are really honored to receive Dr. Mohamed Naim. By the way, this is the second time that he's with us in Metalurgy, so he really loves UNAM, and we are happy for that. So Dr. Naim is a research fellow at the University of Birmingham in the UK, in England too. He also holds a visiting position at the ICES Neutron and Muon Source. So Dr. Naim is an expert in real-time studies. This is in situ studies, mainly neutron diffraction or synchrotron diffraction. So if you ever worry what happened with materials during, for example, a tensile test or a compression test, he's the one that will reply your questions. So before his current role, he was a postdoc at the City University of Hong Kong, and he's also recipient of the Asia and Oceania Neutron Scattering Association Young Research Fellowship. He was the only awardee during the year 2022, right? So he was the only international awardee of this recognition. He organized the first Gordon Research Seminar on structural nanomaterials that was held in Switzerland in the 2024. And he's also organizer of the Symposium on Materials under Extreme Environments at the upcoming International Materials Research Congress that will happen the next week in Cancun, here in Mexico. So he will suffer in Cancun. His research focuses on real-time deformation mechanisms of metallic materials, mainly by neutron diffraction. And today he will talk about his work undertaken during last few years on the mechanical behavior of metallic materials under cryogenic conditions. So we are really honored to receive this talk from Dr. Naim. Please welcome him to the talk.
Thank you so much. Indeed, I'm very happy to be here for the second time. And I really like talking to students, and actually a few of them I'm co-supervising as well, so that's even like a bonus. And so today I will be showing some work. Actually, I will also be talking something about neutron diffraction, in situ experiments, and the work which we did during the last 7-8 years about cryogenic behavior of different materials. Everyone can hear me clearly, right? I mean, you are in the front, of course. Okay, so I put there like how material at extreme cold. What is extreme cold for Mexico City? Yeah. So, I mean, it's a relative term, extreme cold. If we're talking about environmental weather, like Mexico City does not go below, I think, 15 degrees Celsius. In UK, we can go further lower, like close to freezing temperature. Yeah. But the temperature which I'll be showing, I will show some examples, and that will be much, much lower, close to absolute zero, where like some very niche kind of applications happen. So this is what I would be covering. Like, it's like a very non-linear. I will not be like following in this order. There stuff like which like why we need in-service probing of materials, for example. And then I have been using neutron diffraction for like now number of years, and I will like give a bit of background, like why it is unique and which kind of information we can obtain from it. Then applying that to engineering materials. Mainly we are in metallurgy department, so of course it's mostly going to be metals and alloys. And then why we care about materials at cryogenic temperature. which is much lower than, of course, what we usually experience. And then I will show some examples of the work which we've done on multi-principal element alloys, which people also call high entropy alloys for wrong or right reasons. But anyway, we won't get into that, at least not today. And then we can quantify different kind of mechanisms. I think you will be taking some courses where we will be studying about deformation, mechanical behavior, so we can quantify them. Of course, it's not easy task, but we can try up to some extent to deconvolute them and how their differentiation pathway happens. And then I'm very happy that Sandy covered high temperature, so I'll be covering low temperature. And he went from like simple to complex system, I'll be going from complex to simple system. So it's fantastic. Okay, so let's see why we need to have in-service analysis of materials, because we want things to keep running. We don't want to encounter any kind of damage. So I'll give you some examples. Hopefully they can convince you that it's important. So this is one of the example of collapse of twin bridge in Minneapolis in 2007. And it was caused by very thin one of the plate which it was resting on, and which really become thinner like stress concentration. And it resulted in killing like more than 1,000 people and injuring like almost 150 people. Then this is another example which happened. There was this flight which was going from Taiwan to Beijing, and it crashed. Actually, it just like collapsed, I would say, like in midair, and this killed all the people on board, like more than 200 people. This was caused by fatigue crack, just one single fatigue crack which happened, and that was the result. This was the result of that. And then this was a high-speed train accident which happened in Germany in '98, and that was also this wheel of train, like there was a single fatigue crack, and that ultimately led for train to divert from one rail to another one, and ultimately it collided with it just like derailed. I mean, like it just like moved out of the track, and it resulted in like more than 100 people being dead and almost 200 being injured. So these are like really sweet examples. Of course, like these are extremes, but they're like people like got killed and like. But so we do have to have routine maintenance. We do have to take care of these kind of analysis. So one of them which we want, why we need to have, is because we want to have lasting performance. So there won't be any disruption if like the train is going, so it should not have any fall like in midway and you are late for your like class or you're late for your work, right? So second is of course cost, because when any accident happen that result in monetary damages. And above all, it's about public safety, because loss of life like these many people, so that's not affordable. So how we do it, like as metallurgists, we have plenty of tools at our exposure to undertake this task. So this is one example of, say, we have an automobile which is made of some, say, different materials, but composite, titanium, aluminum, number of them, steel as well. So we can do analysis. We can do analysis at multi-scale. We can use, for example, macroscopic techniques, scanning electron microscopy, EBST at micron scale, to look at grain structure, look at features at that level. And then we can go further down to nanometer scale with the transmission electron microscopy, basically to look at dislocation, which Sandy was talking about, because ultimately they are the one which dictate these properties. But then we can go further like to lattice level, and where like crystal structure plays a very important role. So I do diffraction either by neutron or synchrotron, and it is based on a very simple principle which was given by like now more than a century ago, which is Bragg's law, right? This is Bragg equation. And basically what we do, we want to see atomic arrangement in material. And this is a very simple equation. I'm sure like everyone have seen this equation before, 2d sine theta, right? equal to n lambda. So basically it's two things, which is you have some radiation, so in this case X-ray for example, and you bombard it or you shine it on your material, and then you want to make lattice spacing, like how apart these planes are from each other. And from there, like we can predict a lot of, we can see a lot of properties just from there. So this is the same thing, and what we are after is lattice spacing or despacing, and that's the one thing which we get through diffraction. Okay, so I have been doing mainly neutron diffraction, and I will be saying a lot of like good things about neutrons today. They are the best, of course. So we can cover a length scale, a very large length scale, by using neutrons, which can be from femtometer with elementary particles to all the ways like galaxy level stuff, like people probe with that. But for our level is small. For example, you see these motors over here, which is of 1 meter or so. So of course I will give you some details like how we do it and why like they can be used, but it's just to like give an idea. And then also we can do it at different time scale, because we can do analysis, we can do experiments in real time, and so we can also get what we say structure, but we can also get its dynamics as well. So this is basically actually neutron. There were Nobel Prize in '94 on neutron scattering, and one of the guy got it on structure, other one got it on dynamics. By combining neutrons, you can do both kind of stuff. So this is some of the stuff which we can do with not just neutron, but synchrotron as well, but here like it's mainly for a neutron. One of thing is like, as I mentioned, that we can probe lattice spacing with them, and their wavelength is on that range. Then neutrons, as you know, like in say we do electron microscopy, electrons are very, very light particles. Similarly, X-rays, when we do, they interact with electrons. But when we have neutrons, they are neutral particles. So they can go directly into the heart of the atom, which is nucleus. So they interact with nucleus. And because they are heavy, so that's why they can penetrate much deeper. So they are neutral, so they won't be affected by the field around an atom. But also they are heavy, so they can penetrate much deeper. So we can really probe big samples with this. As you have seen with transmission electron microscopy, it's very like you have at the end like really a thin film or like foil like which we'll be looking at. Then we can do non-destructive, like real-time non-destructive at different kind of environment. Then neutrons are very good for light elements because they can have, they are not like how X-rays, which are their interaction increases with increasing atomic number. Here, like they are much different, they're much random. So light element can be probed by neutron diffraction. They can also distinguish because they are neutrons, and isotopes are defined by difference in number of neutrons, right? For example, if hydrogen, deuterium, and tritium, so the only difference is number of neutrons. So because of that, we can also distinguish between different isotopes, which can be very helpful, especially people who work with hydrogen. It can be very helpful. You can also replace, say in polymers, you can replace hydrogen with deuterium to give it a contrast. Then, as I mentioned, like you can study dynamics with it, like energy changes by using this. Then neutrons have magnetic movement, so that's why you can also probe magnetic properties. Then we can implement, because they can pass through a number of materials and they are transparent to certain materials like vanadium, for example. Then you can use like different kind of environment, for example, furnaces around your sample, and still neutrons can go through that to look at whatever you are after. And of course, they are complementary. I mean, we know us often use microscopy, X-rays, and neutrons with each other to like get insights of certain extent, which cannot be brought by maybe another technique. So everything have drawbacks. Nothing is perfect. So with neutrons, the drawback mainly is about they are very, very slow compared to say X-rays. And another thing is like if you want to make like really tiny samples, that can be an issue with it. Then there are some elements which are neutron absorbers. For example, boron is one of the example. which is really a poison, like actually it's used in nuclear reactors to control reactivity of the reactor itself. Then there are different, okay, so you want to get this kind of information, so we have different kind of techniques for that. It's not just one diffraction which you use to get all of this information. So the most common and which I also work with is diffraction. So you can look at, you can get this kind of structure, and you can deduce number of things from that. And we can also not only for metals or alloys, but we can also do it with liquids or with non-crystalline materials as well, something called diffuse scattering. And there have been a lot of work done, especially there was field of metallic glasses where people use a lot of employ this technique to do diffraction. Then Sandy was mentioning about superalloys. So small angle neutron scattering is a good technique to have to see contrast between precipitates and matrix. And also you can look at their morphology, you can look at their size, and so on. Then there is reflectometry, basically, which you look at the surface. Basically, you do concentration of material by probing surface of the material. So if there is gradient of concentration, you can use it for that. Then there is spectroscopy for, say, inelastic scattering, what we call, to look at dynamic behavior of materials. There is also the one which I missed, which is very, very interesting, is imaging as well, where you can like look at different kind of defects or structure in 3D. Okay, so where we get neutrons from? So we have two kind of sources for neutrons. So when neutron scattering field started in 1940s, it was with nuclear reactors, because nuclear power was like coming, and there was also a number of things which was done at different facilities which had neutron sources, nuclear reactors. So in this, what you have a fissile material, and you basically have to have neutron beforehand. So you bombard that on that fissile material, say uranium-235. There are a number of like other combination as well which you can use, ultimately even thorium. So you bombard it and you split, say, uranium atom into two nuclei, and you also get number of, on the average, like 3 neutrons per reaction. And then those 3 neutrons can continue the reaction, and you can also get those neutrons, some of those neutrons, to carry out experiments as well. And some of them get absorbed with moderator and with coolant and so on. So this is one of the example which is Fermi 2 in Munich, Germany. And you see there is this calandria which is filled with water. I think this is heavy water which is used as moderator. And then you have these fuel assemblies inside made of uranium, and ultimately this reaction happen, and you can then have some holes which we call experimental lines or experimental tubes, and you can carry out experiments over there. And this is how a schematic look like. So you have some fissile material inside, then you have some control rods which control this process, and then you have over here beam tube. From there you can get neutron to probe your material. But now the most popular is spallation source, because nuclear reactors, they also pose issue with regard to proliferation, and so also there is issue of radioactivity. So spallation sources are much more safer. But in this you have a heavy nucleus, usually mercury or tungsten, and you bombard a very high energy proton onto it, and it have a cascade reaction where it produce in the form of pulse, like 20 neutrons in one go, and then you will also have some other particles coming out of it. So now most of the facilities which are built around the world, I think UK was the first one which got spallation source, which is called ICIS neutron muon source. And now in US, in Japan, and China, a number of other places as well, they have spallation sources. Then how does it work? So here you see this is for reactor case, which we call angle dispersive neutron scattering. So basically you have a neutron beam which is coming to sample, and then you have detector at different angles, and when these neutrons interact with your sample and they scatter, right, they diffract, and they are collected in these detectors, and from there you get, it's quite similar to actually what you do X-ray diffraction in your lab as well. So the principle is same, but only the radiation is different, and it's much at bigger scale. Then the second one, which is I was mentioning about spallation source based, which we called pulsed based, because it generates a pulse and then like there is nothing and then again a pulse, and the kind of like operation it have is called time of flight. And what we have, so in this case we don't have one wavelength of neutron, but we have kind of multiple wavelength, which we call white beam radiation, which is coming to your sample, and then it is interacting with sample, diffract, and then we collect information in a detector. So this works in a bit, I mean the same Bragg's law applies, but now you have to modify certain things, because here you don't have one single wavelength. So ultimately you can convert it to by using, so this is Planck's constant, so this is momentum, and then ultimately, so this is m is mass of neutron, this is L, which is basically distance from sample to the detector, like how long it take for this neutron after diffraction or scattering to reach to your detector. And this is the equation which ultimately you use. So, but the main thing is still the same. We're after despacing. But in this case, we deduce that from time of flight, which is t over here. Well, all of this is constant. So in this case, we keep angle constant. Planck's constant is there. Then there is length. This is also fixed, and mass of neutrons are also fixed. So these are number of neutron scattering facilities around the world. So there are also some small ones. These are major one, I would say. And you see that some of them are in yellow, which are basically based on reactor, and others are in red, which are based on this pulsed or spallation source base, which are now more common. Any facility which is newly built that is based on mostly spallation source. Then now I mentioned about how neutron are different than radiation. They can distinguish between say isotopes. They are very good for lighter elements. So here is where you can appreciate that. So here you see an X-ray radiation or X-ray beam which is coming and interacting with electrons, while neutrons are interacting with the nucleus, right? And then when they interact, so you see for cross section of X-ray that increases with atomic number, right? So it is easier to probe heavy elements or like high atomic number elements. Then it have its own limitation, like at a certain extent you cannot do much about it. But with neutrons you can see hydrogen have a very large cross section than for neutrons. Then deuterium, which is one of the isotope hydrogen, it is different than hydrogen itself, and then it's not atomic number dependent. So for certain elements it can be very helpful, but others, for example for boron, you cannot choose it unless you want to don't get anything out of it. So I already mentioned they have, because of their large size, large mass, as well as because they interact with neutron, they have high penetration. So but when we do lab XRD, so the penetration is around tens of micron. So basically we're looking at the surface of the material. So you have to prepare your sample. So make sure like it's not just coming from just surface. Then synchrotron we can go, because synchrotron is also X-ray, but it is high energy X-ray diffraction, and you can go to much higher penetration, which is hundreds of microns, so like 1 magnitude of order higher than lab XRD. Then with neutrons, depending on metal, which metal or which kind of materials you are looking at, you can go up to tens of millimeter. So you have to select your material. I mean, like the material you're working, you have to know like if it would be good or not. This is a very simple scattering diagram in real space. So you see, here is polarized is something which is like directing these neutrons. So these neutrons are coming to the sample, which you see over here on a sample holder, and then you can see when they interact with sample, they just go towards the counter, which is detector, where we see, and we know like how much time it takes to reach there. Right. So this is a typical, sorry, that went off. This is typical neutron scattering facility which uses spallation source. This is the one which I have done most of my work so far. It's in Japan, very close Pacific Ocean. It's called JPARC, Japan Protonic CO2 Research Complex. And you see there is accelerator, there is actually two, one 30 GeV and the other one is 3 GeV. And it accelerates this proton, and then ultimately it interacts with the mercury target, and then the neutrons are generated and they are taken to study the material. Then, as I mentioned, that we can have different kind of information from the sample. So they have different kind of beamline. We call it beamline or instruments to do that. Some of them are suitable for doing, as I mentioned, for example, say precipitate superalloys. So we can use, say, small angle neutron scattering. Then there are different others which we can use, for example, for high pressure. For geology people, they use mostly this one. Then there are others as well. But the one which I was using, that is, can I say? Yeah, here, in red, right? So it's called Takumi, which is engineering materials diffractometer. But then how neutrons, I mean, I mentioned about Bragg's law and how I think people know, but how we really see, because we get these peaks. And when we have to study mechanical behavior of materials, how we get that information. So suppose this is our polycrystalline material, and we have grain which are oriented, or crystallite actually, oriented in different orientations. And then you have this radiation which comes, it interacts with your material, and you get a peak, a diffraction peak, which have a position, some intensity, some broadening. So all the information which you'll be getting through these peaks. Okay, then if we apply a force on it, what will happen? This peak can move, right? Depending on if it's tension or it's compression. So this can happen because of the average strain in the material, because your lattice is being stretched now, right? So it's that distortion. Then it can also become broader. So that can tell us something about its subgrain structure. For example, dislocation are generated, they are increasing, dislocation intensity is increasing, or certain other, for example, stacking faults or twins as well. Then we also have intensity. You see that the intensity have now decreased for this blue peak, which is about texture, how the grain are rotating in different orientations. So from these three things, its position, intensity, and its width, we can get really a lot of information. But it's all convoluted, so we have to pull it apart to like see like which one is contributed by what factor. Now this is a typical, say, polycrystalline material. I think this is 304. And here you have grain oriented towards, say, 111 and say 002. And how would that look like on this peak? So you see the first peak, which is all these grains, they are contributing towards this peak. And then these blue ones, they are contributing to the second peak. Right. So basically, by looking at this, we can get information about material behavior. And we can also look at different grain families' behavior during deformation by when the interplanar spacing changes. Now going to the instrument which we use. So in this case, you see that there is this huge machine, but this is on a sample table. So we have a sample table. On top of that, this is loading machine, which we use for cryogenic experiments. And on two sides of it, you see this kind of a structure like conical. It is, these are the detectors. And the neutrons come from from the back of this machine. And they interact with sample in a way, and then they are scattered towards these two detectors. And from there, because there are two set of detectors, so we can get behavior along loading direction when you're pulling, for example, sample, and also transfer to that direction. This is close-up of the machine which we use for cryogenic environments, cryogenic experiments. So here you see like these are those detector banks, and this is neutron beam, and this window is made of vanadium. I mean, steel, it would interact with steel and you'll get peaks or signals for that, but vanadium is transparent to neutrons. So it will just go through that, and then it will interact with a sample, which I will show over here. So this is a sample inside your machine. So here you see that sample is over here, and this is held with these joints, and these are copper coils which are connected to these grips. Basically, and here the temperature is like 4.2 Kelvin, by which we can achieve by this kind of machine. And ultimately through conduction, we get around 15 Kelvin temperature on our sample. So 15 Kelvin is very low temperature, right? It's like much lower than, there are a number of applications actually which do use that low temperature, which I'll come to in a bit. So this is a very simple schematic what's happening. So as I mentioned that neutrons are coming from this side, sample is over here, and then it interacts with sample and it affects introductions depending on loading and transfers, and we get signals in our detectors, and from there we process our data. Okay, so just to give you example at low temperature, again not too low, but this was in 1986 when one of the space shuttle called Challenger, which took off from Florida, that it was in January, by the way. It just took off, and within 60 or 70 seconds, like it collapsed it exploded just like immediately after taking off, within just over a minute. And there was all the astronauts, like all seven of them who were on board, they were killed. And there was a huge controversy about it. They have to cancel a number of programs because of this. And then there was a commission called Rogers Commission, which was made to see what really went wrong. And who knows Richard Feynman? Have you heard of Richard Feynman? No? Okay, so he's a very, okay, I think he's a very interesting guy, really amazing person, and also amazing scientist. So he was one of the members of this commission. And you also see a guy sitting next to, so this is Richard Feynman, and this is another guy, Neil Armstrong. Who knows Neil Armstrong? Okay, cool. Who was he? Yeah, exactly, first person on the moon. So he was also part of that commission, and they were investigating, and Feynman was a genius. So what he did, he took a part of that, so they had these O-rings to seal the different components. So he took a part of that O-ring, and you can see in his hand he's holding this C clamp. So he put it, so he basically took that material, he put it in iced water, like, which is, you can say, 0 degrees centigrade, and then he took it out, and then he put, okay, first he showed like, okay, like put before putting in water, and it was flexible. Then he put in iced water, and then he took it out and put it in C-clamp again, and now he did it, but it was not flexible. So from this he concluded that because on that day temperature was January, was around 0 degrees centigrade, and when that seal become like very brittle at that temperature, it lost this flexibility. That O-ring lost its flexibility. So that was ultimately the reason why this space shuttle exploded. So this is one of the examples. Again, it's not very low temperature, but it can have huge consequences. Then I would just mention, like, very quickly, Sandy already mentioned about the tokamak fusion reactors. Some application where we need very low temperature. So this is a Japan storage 60 tokamak, and I don't know if you can spot some so it lists the temperature. Okay, these are the components, and then it lists some temperature, at what temperature these components operate. For example, this one, yeah, okay, temperature is clear, so it's good. So some component, for example, this thermal shield will operate at 80 Kelvin. Then there are some other components which 50 or 4.5, even like 3.7 Kelvin. Then another on right side, that is European Space Agency's Planck spacecraft, and you can also see then certain components which operate at very low temperature, like it goes from room temperature a bit higher to around 36 Kelvin. So especially in space exploration, in nuclear application, similarly superconducting magnets, they operate around 4.2 Kelvin. They become superconductor at that temperature. Then one of the application is magnetic resonance imaging, which also use cryogenic temperature. Then another application is, for example, transportation and storage of liquid gases. One of the best example is liquid hydrogen, because now hydrogen economy is like moving like really forward, and the liquid hydrogen exists at 20 Kelvin. So we need material which can handle them at that temperature. And already there is plan by Airbus that they would like to install a liquid hydrogen tank inside their plane. So let's see how it materializes. Okay, so now I will show you, I work with these so-called high entropy alloy or multi-principal element alloys, which Sandy also showed one of the example, which was the first work which was published. The first. So this is, you can see that when you decrease temperature, material becomes stronger. Does anyone know why? Quick. Okay. Okay, we'll come, we'll ask later maybe. So, because of dislocation, I mean, everything about deformation is about related to dislocations. So basically, dislocation movement become difficult, so they become less mobile. And there are a number of other factors that I will not go into detail, but anyway, so material becomes stronger at low temperature. Their yield strength increases, but their ductility usually decreases. And some material even have, as Sandy was mentioning, even become brittle at low temperature. They have ductile to brittle transition temperature. But usually FCC, phase and cubic materials don't have that kind of issue. But usually they don't show increase in ductility, but this was surprising that at 77 Kelvin, there is not only increase in strength, but also significant increase in ductility. And there was, it maintained its fracture toughness. And they associated, this was work from Rob Ritchie and Iso George, people from Oak Ridge and the Lawrence Berkeley National Lab. And they associated this increase in ductility and increase in strain hardening with deformation twinning. So at room temperature, it had only dislocation slip, but at low temperature, it had also twinning. So these two mechanisms ultimately contributed to better mechanical properties. All right, so I already mentioned that. So now how these mechanism changes, that depend on something called stacking fault energy, which is material dependent, but it also depends up to a certain extent on temperature if you have the same material. So this is for austenitic steels, for example. So if you have stacking fault energy up to, okay, say 40 Kelvin or so, is mainly dislocation slip, 40 millijoule per meter square, pardon. But if you go below that, now you can activate deformation twinning. And if you go further down, then you can have martensitic transformation, and it can depend on temperature as well. So you can control with that. You can have a different behavior depending on temperature. When this paper was published in 2014, which I shown in the previous slide, that at cryogenic temperature they have twinning activated at 77 Kelvin. So there was this paper coming from I think KTH in Sweden, where they did some calculation and they predicted that if you go to further low temperature below liquid nitrogen, below 77 Kelvin, you would have phase transformation as well. So in addition to twinning. So that was when we did, so that we wanted to see like what happened. So we did in situ experiment with neutron diffraction, and we did it 15 Kelvin. And indeed we see that there is increase in strength, also increase in ductility in the same alloy which they were working on. And but when we look at diffraction patterns, of course there is peak position changes there, they become broader, their intensity changes, but we don't see any new peak related to the second phase which is coming out. So there is no phase transformation in this case. So this study which we published now like 4 years ago, the main thing was that like there was something wrong with those calculations. So indeed they revisited them and they forgot, they did not contributed vibration entropy into that, how significant role that can play at low temperature. So then I would not go into too much detail about this because I think this is too technical. I would just like to give an overview which kind of information you can obtain from it. So we can get to this lattice strain, which is the upper panel, and we can see these are different orientations or different peaks and how they behave, how their position changes, basically relative position change with stress. While this is on the bottom panel, this is what we call texture. In this case, it is represented with peak intensity, normalized intensity. And this is typical for FCC, where grain more rotate towards 111 and they move away from 220. So you see over here is their intensity is increasing, while 220, which is this blue one, is almost diminished at the end. Now, if we go to low temperature, we see some difference. So here you see this pink and the black, they were overlapping. Actually, you cannot see black at all, I think. But here you can see there is separation between these two. Similarly, this red and this green, and again you see separation at high stress. And also there is a change in how this texture evolved. So initially it is increasing how it was over here, but at the end it almost saturates. So from this difference of lattice strain between the same family of planes, we can obtain something called stacking fault probability, because this difference is given by how the FCC is arranged. Like I think we know arrangement of FCC, like how like the from this sphere model, like how like ABC like, right, this repetition of lattice. But if you remove a layer or if you insert an extra layer at a certain point, that's what we call stacking fault. So by splitting of these two peaks, we can obtain stacking fault probability. And you can see that blue, which is at room temperature, 295 Kelvin is room temperature, that does not change. I mean, very little change. The 15 Kelvin one, that you can see it's increasing with stress. Similarly with texture, which is I represented over here 111, which is the main where like the grain rotate towards 111 for FCC materials. So you see for this room temperature is increasing linearly, while for low temperature it have a very different kind of trend. And from this we can basically tell deformation pathway of material, and we can relate it with to like, okay, initially it was mainly dislocation, then there was stacking fault, then there is something else happening at the end as well. So basically we try to answer questions about deformation pathway and try to understand what is happening with material at a low temperature. So this is the same diffraction peak, but it's shown in 2D. So how they are changing with time. And from this we can, they have deformation signatures, so-called. So I put here for 3 temperatures, and you can see at room temperature how the peaks are more symmetrical. They become broad at different strain, but not that broad. But when you go to say 25 Kelvin, you see there is like quite asymmetrical broadening, right, over there, and they have much more broadened than at 295 Kelvin. And this is very simplistic what I'm going to say, but somehow like things, you have to make things simple in order to really deconvolute. So the relative peak shift is usually associated with stacking faults. Then if the peak broadening, that's basically signature of dislocation density increasing. And if you have this asymmetrical broadening, that's related to twin faults. And then we can quantify these by using certain models or equations. And then again, like this is what I've shown for a different alloy which had 5 elements, and then now this is for 4 elements. So we started with 5 elements, and then we removed manganese, and this one also have quite similar behavior. And then we can quantify contribution at different temperatures with stress. For example, at dislocation density increases at low temperature, twin fault probability also increases, but it have very different behavior for 40 and 25 kilometers, very close temperatures. And then stacking fault probability also increases at low temperature. Then we went now from 4 elements to 3 elements. So we removed iron, and then we see what happened. So this was the alloy where we could see Martin-City transformation, like there is this small peak which is coming, which belong to HCP, hexagonal close back structure, from FCC to SCP, which have its own contribution. Okay, then so these are 3 examples where multiple deformation mechanisms are happening. There is, of course, dislocation slip. There is also twin faults or stacking faults, but also Martin-City transformation for chromium, cobalt, nickel. But then there was this report about vanadium, cobalt, nickel, where vanadium have much larger size and much higher misfit volume. and it can have much higher yield strength because of that. So we were very interested in that material, and we used one of the material which is like not that fine grain size, bit coarser grain size, and it also showed increase in strength and ductility. But it was very peculiar for this example. You see at room temperature on the left and 15 Kelvin, that I have shown that these two 111 and 222, they overlap at room temperature, for example, for the first case which I shown you. But here, even at low temperature, it have very similar trend. And with the TM, we also found that it's only dislocation slip. There is no stacking fault, there is no twin faults. And then we quantified its dislocation density, and it shown a very interesting trend. So it had kind of like two-step kind of dislocation density accumulation and dislocation accumulation. But so one is like slower, and the second one is faster. But the faster one start earlier for low temperature. And because of that, we have also, because dislocation density is higher at low temperature, and also it starts earlier, so you have higher strain hardening rate for this one. So this work is still unpublished, but we think it's very interesting that this one have only one mechanism, because the claim was the first paper when it was published, and since then people have been saying that when you have multiple deformation mechanism, you can have increase in ductility and strain hardening. But in this case, it is only dislocation slip, but still you see increase in ductility as well at low temperature. Then these were the examples which so-called medium entropy alloys or high entropy alloys. I was co-supervising a student at University of Hong Kong, and we thought about looking at conventional systems or more simple systems which are more understood. So there was a student, Human Ma, PhD student, and her thesis was based on understanding mechanism in these kind of alloys. So one was 316L steel. So same, if you look at the 316 steel, its testing curve, so it does not become brittle at low temperature, it has significant ductility, but it does not increase. But if you look at its strain hardening, like how much it harden or work hardening, what we call, it's very significant compared to room temperature. So now you look at these diffraction patterns, this map, and these are along two, one is for loading direction, one is transformation. You remember, like I mentioned, that one is for loading, one is like normal to that. And in this case, I have shown the previous example where like the same peaks were changing, but there were no new peaks. But here you see that, for example, over here, I don't know if you can see my pointer, I think you cannot. But you see some new peaks are coming, right? For example, between around after 2 angstrom or so, there is these new peaks. Then another one like appearing over here. So initially it was FCC, phase center cubic, but then it also have, in the transfer section, you also see at CP peaks like this epsilon phase, and also alpha prime, which is a BCT martensite phase. And then we can quantify contribution of, now this is kind of like what Liliana also worked with this heterostructure material, but this is a heterogeneous material, like kind of composite as well, because it have HCP, BCC, FCC, and in this you can see that which one is contributing more towards ultimate stress. So these are phase stress for FCC, HCP, and BCC. So BCC is the one which is more contributing this high strain hardening, and also dislocation density is much higher. So you see FCC is these black ones, and much higher in BCC over here, these red one, and HCP it appears and then it disappears. So we also try to understand mechanism like how FCC to HCP to BCT, how this mechanism or how this transformation is happening. So this was published just a few months ago, I think 3-4 months ago in ACTA, and it was very interesting study. Then another project of her was looking at cobalt nickel, because we were going up to chromium cobalt nickel ternary element, and now we wanted to simplify it to understand mechanisms, because it's much easier to do in simple elements, maybe not that easy still, than like really complicated systems. So this was, we picked one system cobalt nickel, which was FCC. Cobalt 35, nickel 65 is in atomic percent. And this is very simple system, because this increase in ductility was somehow associated with these multi-component high entropy alloys. But this is very simple system. but still you see increase in strength as well as ductility at low temperature. And this was very interesting to us. And in this case, again, like we quantified different kind of mechanism, and at low temperature, this equation density becomes significantly higher. We have very high twin fault probability, but also there is martensitic phase transformation, which is happening in this case, which is contributing to very high strain hardening rate, but also these mechanisms which is coming together to give rise to higher ductility as well. Then we also worked on heterostructured stainless steel, which was with Dr. Liliana. And in this case, we did experiments at room temperature and 77 Kelvin. So heterostructure, I think you can, you already know her, and you can talk to her about it. This is heterostructure material, which have different magnitude of these kind of grains, like very fine, very coarse, not very coarse, but like very fine and a bit coarser. And it have a very interesting results. So because it was heterostructured and it had a very high yield strength, because usually with steel you have 200, 300 megapascal yield strength. But of course, like you have to sacrifice something, but still it have a reasonable ductility. But when you go to low temperature, we have increase in strength, but also look how much the ductility has increased. So that's really amazing. So again, this work is not published yet, so it's like preview. Here, like you can see comparison of yield strength of normal steels and here heterostructured stainless steel. So it's very high at 70 as factor of temperature, but this one is for 77 K. And again, the reason for this is we did also in situ neutron diffraction, and you can see different phases coming out, including SCP little bit, but then it is disappearing. You see, there is no peak over here, then there is this tiny bump over here, then it disappears again. And then also there is alpha prime phase as well. And how it changes with the deformation, there is basically you can see that how this phase is coming and then going, and these two are changing. So alpha prime is going on behalf of gamma. Okay, so now just to give you last kind of teaser, and like I think I will stop here. This is what we wanted, because we do experimental stuff. We don't, at least like when I was working with PUS group, we don't do any kind of simulation. But then there was a group of Marcel Sommers at Denmark Technical University, and he had a student who was working on simulations by ab initio and the DFT and the MD simulation. And the question was, when they do simulation, the stacking fault energy is negative. But when we do experiment, it's always positive. What's the reason? Like how we can bridge this negative and positive stacking fault energy from simulation and experiment. So this was student Konstantin who was working on this, and it was ultimately was part of his thesis. So we have this work just published, actually fresh out of oven, just like published last week, and we were very happy about it. And just I will not go into detail, but basically we combine DFT and the in situ experiments, and because otherwise you have to do a lot of experiments with TM sample, and you have to see which mechanism is coming, and you deform in steps. But in this case, in situ, we try to bridge this gap between positive and negative, positive values from diffraction and negative values from DFT. Okay, so I will just stop here. I will just say like what we can achieve with this kind of experiments. So we can probe bulk behavior, right, at extremely cold environments, and also extremely high temperatures as well, are different kind of environments. We can also pinpoint activation of different mechanisms because it's in situ in real time, so you can see when something is coming out. For example, you see this phase at CP which is coming out at certain point and is disappearing. Then we can also have this whole deformation pathway, and we can also quantify mechanism. It's much more complicated, but still you can have a decent idea of what is going on, how much is contributed by different mechanism. And we can also somehow, how like I have shown last example, I did not mention it, we can try to combine it with simulation, and also we can give feedback for the alloy design. So I'll stop here, and I'll be very happy to have some questions.
So thank you so much to Dr. Naim for the excellent talk. So we have some time, some minutes for questions and answers. You can ask in English or in Spanish, and I can translate for you. Pueden preguntar en español si quieren, okay? So, okay, Brenda, please.
Hi, thank you for your presentation. What other advantage is there to working at low temperatures besides increasing resistance?
Sorry. That's interesting question. Okay, so one of that could be superconductivity, because materials like don't, I mean, there have been like recently very huge controversy about like people trying to make superconducting materials at room temperature, like at high temperature. But usually materials have superconducting properties at very low temperature, close to like 10 Kelvin, even like sometime like even lower than that. I mean, in that line, like 10, 20 Kelvin, something like that. So, which does not exist at room temperature, but that can exist at very low temperature. Similarly, magnetic properties. We did some work where like we saw transformation of this, one of the alloy which we have seen, showing paramagnetic behavior at low temperature. So these are the some which I can think on top of my head. Yeah.
Thank you.
Thank you. Some other question or comment? No? Yeah, okay.
Hello, I am Marco. Marco. I'm going to ask in English because I have writing my question, and is why some materials have present higher ductility at low temperatures than the room temperature?
Why they have a high ductility at low temperature?
Repeat, please.
So you're asking why they have higher ductility at low temperature than room temperature?
Yes.
Okay, that's yeah, that's the question. Okay, so it's really hard to answer, to be honest. I mean, because it's not to like when this paper was published in 2014, where they have shown that in this alloy at room temperature they had only one mechanism, deformation mechanism, which is distribution slip. But when you go to low temperature, you also activate what is called deformation twinning. So because of that, they cooperate, and somehow you can delay, because when you start deforming material, ultimately you have these neck formation, right? You form a neck, and then ultimately your material will like fracture. So their argument was when you have deformation twinning, you delay this necking instability, right? This is kind of instability ultimately which break the material. That was their argument. But now we have seen like the example which I've shown like before going into conventional system, that in this vanadium cobalt nickel there is also just one simple distribution slip mechanism, but still it increases ductility. But it's not the only one. People actually was working in 1960s on single crystals. There are a lot of literature on aluminum single crystals, for example, where people seeing exactly the same thing. When you go to low temperature, you have higher ductility. So probably because of dislocation interaction, because an aluminum have very high stacking Fall energy, so you cannot activate another mechanism. So it have to do with dislocation dynamics then. How dislocations, their character, that can change, like it can be screw edge or mixed type. It can also be about, they can form dislocation cells, and also about we accumulate more dislocation at low temperature. So ultimately everything is linked to dislocations, but there is no simple answer to that. It's very like difficult, like say, because different materials behave differently. Even like single element, like they are showing increase in ductility.
Thank you. Some other comment or question? Pueden preguntar en español si quieren. Okay, 1 minute. There.
Do we get the superconductive properties in every high entropy alloy?
Simple answer, no. I mean, no, we don't get superconductivity, I mean, as far as I know. because you have to have a certain kind of arrangement in material or certain kind of element which can give rise to that properties. So no, it's like specific materials which are specific element which you have to have to lead to that superconductivity. No, at least like the one which I have shown, I have not seen any report about any of these showing superconductivity.
But we do get an improvement in the conductive properties.
Yeah, of course. I mean, that's very simple. You don't have to go to like any temperature. When you go to high temperature, conductivity usually decreases because it's about how the atomic bonds, like that's how it is linked, right? So, yeah, you would have improvement, but it's not like that magnitude of improvement. I don't know, like I don't have value for that. I have not looked into that. But yeah, I would suspect like it increases a bit. Conductivity, thermal conductivity, not superconductivity, yeah.
Wouldn't that be like an obstacle to use that type of materials like for structural purposes at low temperature, of course?
Yeah, you're saying like, would that be okay to use it for structure materials?
Yes, if they are like better at conducting temperature or maybe electricity.
No, but yeah, right. Yeah, that's a good point. But that happened to all the materials, right? Because it's about this atomic bond, like how they interact with each other. But it's not, as I said, like it's not a huge difference in, I would say, thermal conductivity. And of course, it depends, like when you are selecting for, say, these niche applications in aerospace, you have to consider not just one factor, you have to look at all the factors, their connectivity, their density as well, their like strength and so on. So no, it's not a simple factor like just you can say that, but yeah, you have to consider that ultimately.
Okay, thank you.
You're welcome.
Thank you. Some other question, comments? Yeah, please.
Hi, my question is what kind of applications are used right now for these materials at low temperatures? Are there any real applications in the real world right now?
Yeah, excellent question. So I've shown you, for example, one of the examples definitely is widely used, which is steel, 316L steel. But I think your question is about high entropy alloys, so-called high entropy alloys. So at low temperature, at cryogenic, these materials, like I have not seen so far any application. So we are studying more kind of fundamentals. I mean, like I'm at least study fundamentals. I am not aware of at least so far, like if they are being used. Maybe I hope in the future they will be used, but at the moment I don't know if they are really used. But it takes time ultimately. But you also have to think about other factors, for example, cost, because some of these elements are expensive. I mean, ultimately you take this 5-element alloy called Kent alloy, and you take steel. They can have quite similar properties. You can manipulate the macrostructure, which is much better option. And you can have similar properties, but arsenic steel will be much cheaper than Kent alloy itself. So you also have to think about that. But hopefully they will have some applications.
Thank you.
Thank you. Some other comment, question? Yeah? Okay, 1 minute. I will pass from here.
Following the question, I want to ask, I know the temperatures we're talking about, it's so lower, but could we use that alloys for underwater exploration? I mean, they will resist corrosion and the pressure of the ocean?
Okay, that's an excellent question. So when we put any material, that's an excellent question, because we do have to think about not just like one, because I'm here talking about mechanical properties. They have amazing mechanical properties even. Then you have to look at other factors. You have to look at its corrosion resistance. And also in that environment, not just because different kind of like seawater will have much different corrosion resistance compared to the water which, say, we use at homes. So of course you have to look at its corrosion resistance. You have to otherwise, like, it's not just mechanical properties which matters ultimately. Simple. So again, like I don't think it will be wise to use them for those kind of applications, given just the cost itself, and also because when you have so many elements, of course you can make in a lab in a very homogeneous state, but it's on a different level of challenge when you have to build like these massive pipes, and this is complex. I mean, a structure which they form, so it will be a challenge in itself.
Thank you.
Thank you. I think because of time, we can go for one last question or comment. Somebody wants to comment or ask something? No? Okay, the last one. 1 minute. So I saw the face of Angel just waiting that no one else will ask. Okay, Angel, please.
Esta vez en español. ¿Han alguna vez probado o bueno, son compatibles las aleaciones de alta entropía y los heteroestructurados para hacer algo?
Okay. The question is if heterostructure materials and high entropy alloys are compatible to design some application, some industrial application.
Yeah, of course. Lily can answer in a better way, I think. But yeah, we actually have worked. Other people also worked on it, where they need high entropy or medium entropy alloys into heterostructure. I mean, it's just an alloy. You can generate heterostructure into it, but there are a number of rules for that, for something to be heterostructured. And one of them is like you have to have pain and slip in them, right? So these kind of factors you have to consider. Otherwise, yeah, you can make heterostructure out of high entropy alloys. Yeah, nothing is stopping it. Yeah, good.
Thank you so much. So please thank again to Dr. Naim for this excellent talk. And we have some gifts for him. So some notebook with the logo of UNAM and some nice thermo for him also. So thank you so much. Okay. And now Dr. Naim will make a question. So the student that will reply the question will win like this beautiful cup. So Dr. Naim, you can ask. All yours.
Okay, I had to think question. I've forgotten about that. Okay, I think I can ask just from fundamentals. So I mentioned about stacking fault. Actually, I mentioned a lot about stacking fault. Does anyone know what is the difference between intrinsic and extrinsic stacking fault?
What is the difference between extrinsic and intrinsic stacking fault? ¿Cuál es la diferencia entre fallas de apilamiento intrínsecas y extrínsecas?
Okay. Come on.
Come on, you can do it. Okay. You want to wait or one more? Professor Gonzalo? Okay, Professor Gonzalo.
This is a good learning point, yeah. Yeah, can I have the cup?
Yeah, so the cup is to Dr. Naima. No. No, okay. One next question.
Okay, who can name, some other kind of faults in a material?
Some what?
Some other faults, like stacking fault, but there are also other faults.
Okay.
Maybe I have mentioned some of them, but...
Okay, name different faults.
Okay, but you have to name like at least 3.
Okay, he's difficult. Okay, la pregunta es si pueden decirle qué otro tipo de fallas puede haber en un material. O sea, que mencionen los tipos. Fallas, ajá.
I think we should learn them, right?
No estamos hablando de fractura, ¿eh? Es como fallas de apilamiento, fallas planares.
Any kind of defect.
You? Okay. Okay, Eduardo wants to try, okay.
Podría ser de borde, edge and twin, de tornillo, de borde y de... ¿Sí, no? Okay.
The reply, he say that is edge screw, and twins.
Okay, I mean those are dislocation, but okay, yeah, cool.
But okay, it's valid. Okay, so thank you so much again to Dr. Naim and also to Professor Sandy for these excellent talks. So if you can come in front, we can take a group picture, like all together. So please come in front, and Dr. Naim and Professor. Yeah, you can put like your talk.
No,
So-
is there a post like which you can put? I think
Poster. Oh no.
Okay.
Maybe you can look for the logo for them. I didn't think on that. But you can put anything.
Okay.
Your face.
Okay, then we can have quick like.